Now we can model the velocity of our oscillator. Our reference point moves around the circle, and at any position it has a velocity tangent to the circle. In other words, for a very short time interval around this position, it's moving like from here to here. That's along the direction of this velocity vector, or very close to the direction of this tangent vector that I've drawn here. So our velocity vector on the reference circle looks like this, and I'm going to go ahead and color that in purple. And I'll note that the magnitude of the velocity vector is just omega times a, because if we multiply the number of radians per second by the radius of the circle, we get the speed of the point as it moves around the circle. And hopefully we're clear on that at this point. Okay, well, this velocity vector is tangent to the circle. This vector is radial. It goes from the center of the circle out to the point where the velocity vector is tangent, so that these two vectors make a right angle. That means that, well, let's see, this angle here is theta. Okay, so if I was to extend this line out, I would still have an angle theta as I came around to that line. So the angle between this horizontal dotted line here and this direction is theta. We have to go another 90 degrees to get to the v vector, so that the angle of the v vector is theta plus 90 degrees. And there we have that. If we project this v vector down to the x-axis, the initial point projects down to here, the same point on the x-axis, but it doesn't really matter if that's the same point on the x-axis, because velocity is not a position. That's a little bit of a digression. Ignore that for the moment. So the velocity vector can project down to here, and the tip, the initial point will project to here, the tip will project to here, so that this vector here will represent our x velocity. Now, velocity and position aren't the same kind of quantity, so the length of this vector is not a length on an x-axis. It's just a vector that's floating out here with some scale. We haven't scaled this picture, and we don't want to talk too heavily about scaling, because we tend to lose people in a general or principles of physics course when we do that. It's a little beyond the scope of what we expect people to understand. Okay, the point is that projecting this vector onto a horizontal line is going to give us a vector that can represent the velocity of our object. So the object is here, and it has this velocity. Now, what's going to happen as we rotate around a little further? Well, this velocity vector is going to get more and more vertical. The more vertical the velocity vector gets, the shorter its projection is going to be down here. So that this velocity vector will be shrinking as we move from here to here. This x vector will be getting bigger, the velocity will be getting smaller. Well, doesn't that represent what happens to a harmonic oscillator as it goes through the equilibrium point, moving its maximum speed, and then it moves out toward its most distant point, its extreme distance from the equilibrium position, slowing down. So it's moving pretty fast here, slowing, comes to a stop, and it turns around, goes back, and it starts repeating that. So as the position gets bigger, well, that happens as the x vector gets bigger, the velocity vector is going to get smaller. And this model accomplishes exactly that. Now, a point moving around a circle has a centripetal acceleration. Centripetal acceleration is going to be v squared over r. Now, since V is omega times A, V squared is omega squared A squared, and this is going to become omega squared A. The radius of the circle is A, of course, so it's V squared over R becomes quantity omega A squared over A, which is omega squared A. So we have a centripetal acceleration. So this point is accelerated back toward the origin. And I'll represent that acceleration by this vector. We can project this vector on down, and we get our A sub x, our acceleration component in the x direction, and this will be the actual acceleration of our oscillator. Now, the further we get from equilibrium, the more horizontal these vectors get, so the more horizontal the centripetal acceleration vector will get. So the centripetal acceleration vector is biggest when the reference point is out here, when the position of the oscillator is at its negative A position. When the velocity has reached zero, the acceleration will have its maximum magnitude. This acceleration vector will grow as we move from here to here. Now you might not see all of that, but that is the picture, and in our next class we'll discuss the picture in a little more detail at a little greater length.